Hello friends, in the last lecture we discussed that the goal of statistical thermodynamics is to understand and to interpret the measurable macroscopic properties of materials in terms of the properties of their constituent particles and the interactions between them. Then we learned the basics of black body radiations through Stephen's law and the Wien's displacement law. In today's lecture, we will prove that the characteristics of black body radiation cannot be explained using classical concepts. So, we start by discussing one of the early attempts of using classical ideas to explain the concept of black body radiations and then move on to the Planck's hypothesis. Rayleigh-Jean's law. To describe the distribution of energy from a black body, we define I lambda T into d lambda to be the intensity or power per unit area emitted in the wavelength interval delta lambda. The result of a calculation based on a classical theory of black body radiation known as Rayleigh-Jean's law is I lambda T is equal to 2 pi C Kb into T upon lambda to the power 4. Here Kb is the Boltzmann's constant. The black body is modeled as the hole leading into a cavity, resulting in many modes of oscillation of electromagnetic field caused by accelerated charges in the cavity walls and the emission of electromagnetic waves at all wavelengths. In the classical theory used to derive equation A, the average energy for each wavelength of the standing wave modes is assumed to be proportional to kBT based on the theorem of equipartition of energy. An experimental plot of the black body radiation spectrum together with the theoretical prediction of the Rayleigh-Jean's law is shown here. At long wavelengths, the Rayleigh-Jean's law is in reasonable agreement with experimental data, but at short wavelengths, major disagreement is apparent. As lambda approaches 0, the function I lambda T given by equation A approaches infinity. Hence, according to classical theory, not only should short wavelengths predominate in a black body spectrum, but also the energy emitted by any black body should become infinite in the limit of 0 wavelength. In contrast to this prediction, the experimental data plotted in figure shows that as lambda approaches 0, I lambda T also approaches 0. This mismatch of theory and experiment was so disconcerting that scientists called it the ultraviolent catastrophe. Planck's law. In 1900, Max Planck developed a theory of black body radiation that leads to an equation for 1 into lambda T that is in complete agreement with experimental results at all wavelengths. Planck assumed the cavity radiation came from atomic oscillators in the cavity walls. Planck made two bold and controversial assumptions concerning the nature of the oscillators in the cavity walls. The energy of an oscillator can have only certain discrete values En, that is, En is equal to NHF. Here n is a positive integer called a quantum number. A quantum number is generally an integer that describes an allowed state of a system, such as the values of n describing the normal modes of oscillation of a string fixed at both ends. F is the oscillator's frequency. H is a parameter Planck introduced that is now called Planck's constant. Because the energy of each oscillator can have only discrete values given by equation B, we say the energy is quantized. Each discrete energy value corresponds to a different quantum state represented by the quantum number n. When the oscillator is in the n is equal to 1 quantum state, its energy is hf. When it is in the n is equal to 2 quantum state, its energy is 2hf, and so on. The oscillator emit or absorb energy when making a transition from one quantum state to another. The entire energy difference between the initial and the final states in the transition is emitted or absorbed as a single quantum of radiation. If the transition is from one state to a lower adjacent state, say from n is equal to 3 state to n is equal to 2 state, equation B shows that the amount of energy emitted by the oscillator and carried by the quantum of radiation is E is equal to hf. An oscillator emits or absorbs energy only when it changes quantum states. If it remains in one quantum state, no energy is absorbed or emitted. This figure here is an energy level diagram showing the quantized energy levels and allowed transitions proposed by Planck. This important semi-graphical representation is used often in quantum physics. The vertical axis is linear in energy and the allowed energy levels are represented as horizontal lines. The quantized system can have only the energies represented by the horizontal lines. The key point in Planck's theory is the radical assumption of quantized energy states. This development, a clear deviation from classical physics, marked the birth of the quantum theory. Planck's wavelength distribution function. In the Rayleigh-Jeans model, the average energy associated with a particular wavelength of standing waves in the cavity is the same for all wavelengths and is equal to kBT. Planck used the same classical ideas as the Rayleigh-Jeans model to arrive at the energy density as a product of constants and average energy for a given wavelength, but the average energy is not given by the equipartition theorem. A wave's average energy is the average energy difference between levels of the oscillator weighted according to the probability of the wave being emitted. This weighting is based on the occupation of a higher energy states as described by the Boltzmann distribution law. According to this law, the probability of a state being occupied is proportional to the factor R into e to the power minus k upon kb into t, where E is the energy of the state. At low frequencies, the energy levels are closer together as on the right, and many of the energy states are excited because the Boltzmann factor is relatively large for these states. Therefore, there are many contributions to the outgoing radiation, although each contribution has very low energy. Now, consider high frequency radiation, that is, radiation with short wavelength. To obtain this radiation, the allowed energies are very far apart on the left. The probability of thermal agitation exciting these high energy levels is small because of the small value of the Boltzmann factor for large values of E. At high frequencies, the low probability of excitation results in very little contribution to the total energy, even though each quantum is of large energy. This low probability turns the curve over and brings it down to zero again at short wavelengths. Using this approach, Planck generated a theoretical expression for the wavelength distribution that agreed remarkably well with the experimental curves. This function includes the parameter h, which Planck adjusted so that his curve matched the experimental data at all wavelengths. The value of this parameter is found to be independent of the material of which the black body is made and independent of the temperature. It is a fundamental constant of nature. At long wavelengths, this equation reduces to the Rayleigh Jeans expression, and at short wavelengths, it predicts an exponential decrease in I lambda t with decreasing wavelength in agreement with the experimental results. When Planck presented his theory, most scientists, including Planck, did not consider the quantum concept to be realistic. They believed it was a mathematical trick that happened to predict the correct results. Hence, Planck and others continued to search for a more rational explanation of black body radiation. Subsequent developments, however, showed that a theory based on quantum concept had to be used to explain not only black body radiation but also a number of other phenomena at the atomic level. The quantum particle. Because in the past we considered the particle and wave models to be distinct, the discussion we just had may be quite disturbing. The notion that both light and material particles have both particle and wave properties does not fit with this distinction. Experimental evidence shows, however, that this conclusion is exactly what we must accept. The recognition of this dual nature leads to a new model, the quantum particle, which is in combination of the particle model and the wave model. In this new model, entities have both particle and wave characteristics, and we must choose one appropriate behavior particle or wave to understand a particular phenomena. In this section, we shall explore this model in a way that might make you more comfortable with this idea. We shall do so by demonstrating that an entity that exhibits properties of a particle can be constructed from waves. Let us first recall some characteristics of ideal particles and ideal waves. An ideal particle has zero size. Therefore, an essential feature of a particle is that it is localized in space. An ideal wave has a single frequency and is infinitely long as suggested by this figure. Therefore, an ideal wave is unlocalized in space. A localized entity could be built from infinitely long waves. Imagine drawing one wave along the x axis with one of its crests located at x is equal to 0 as shown at the top of this figure. Now draw a second wave of the same amplitude but a different frequency with one of its crests also at x is equal to 0. As a result of the superposition of these two waves, beats exist as the waves are alternatively in phase and out of phase. The bottom curve in figure shows the results of the superposing of these two waves. Notice that we have already introduced some localization by superposing the two waves. A single wave has the same amplitude everywhere in space. No point in space is any different from any other point. By adding a second wave, however, there is something different about the in-phase points compared with the out of phase points. Now imagine that more and more waves are added to our original 2, each new wave having a new frequency. Each new wave is added so that one of its crests is at x is equal to 0, with the result that all the waves add constructively at x is equal to 0. When we add a large number of waves, the probability of a positive value of a wave function at any point x not equal to 0 is equal to the probability of a negative value, and there is deconstructive interference everywhere except near x is equal to 0, where all the crusts are superposed. The result is shown in this figure. The small region of constructive interference is called a wave packet. This localized region of space is different from all other regions. We can identify the wave packet as a particle because it has the localized nature of a particle. The location of the wave packet corresponds to the particle's position. The localized nature of this entity is the only characteristic of a particle that was generated with this process. We can always prove that this wave packet can achieve particle characteristics such as mass, electric charge, and spin. The uncertainty principle. Whenever one measures the position or velocity of a particle at any instant, experimental uncertainties are built into the measurements. According to classical mechanics, there is no fundamental barrier to an ultimate refinement of the apparatus or experimental procedures. In other words, it is possible in principle to make such measurements with arbitrarily small uncertainty. Quantum theory predicts, however, that it is fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. Werner Heisenberg introduced this notion, which is known as the Heisenberg uncertainty principle, which states that if a measurement of the position of a particle is made with uncertainty delta x and a simultaneous measurement of its x component of momentum is made with uncertainty delta px, the product of the two uncertainties can never be smaller than h bar by 2, that is delta x into delta px is greater than and equal to h bar by 2. This means it is physically impossible to measure simultaneously the exact position and exact momentum of a particle. Heisenberg was careful to point out that the inescapable uncertainties delta x and delta px do not arise from imperfections in practical measuring instruments. Rather, the uncertainties arise from the quantum structure of matter. To understand the uncertainty principle, imagine that a particle has a single wavelength that is known exactly. According to de Broglie relation, lambda is equal to h upon p, we would therefore know the momentum to be precisely p is equal to h upon lambda. In reality, a single wavelength wave would exist throughout space. Any region along this wave is the same as any other region. Suppose we ask, where is the particle? No special location in space along the wave could be identified with this particle. All points along the wave are the same. Therefore, we have infinite uncertainty in the position of the particle, and we know nothing about its location. Perfect knowledge of the particle's momentum has cost us all information about its location. In comparison, now consider a particle whose momentum is uncertain, so that it has a range of possible values of momentum. According to the de Broglie relation, the result is a range of wavelengths. Therefore, the particle is not represented by a single wavelength, but rather by a combination of wavelengths using this range. This combination forms a wave packet as we discussed earlier. If you were asked to determine the location of the particle, you could only say that it is somewhere in the region defined by the wave packet, because there is a distinct difference between this region and the rest of the space. Therefore, by losing some information about the momentum of the particle, we have gained information about its position. If you were to lose all information about the momentum, you would be adding together waves of all possible wavelengths, resulting in a wave packet of zero length. Therefore, if you know nothing about the momentum, you know exactly where the particle is. The mathematical form of uncertainty principle states that the product of the uncertainties in position and momentum is always larger than some minimum value. This value can be calculated from the types of arguments discussed earlier, and the result is the value of h bar by 2 in this equation. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. The characteristics of black body radiation cannot be explained using classical concepts. Planck introduced the quantum concept and Planck's constant h, where he assumed atomic oscillators existing only in discrete energy states were responsible for this radiation. In Planck's model, radiation is emitted in single quantized packets whenever an oscillator makes a transition between discrete energy states. Some experiments can be explained either better or solely by particle model, whereas other can be explained either better or solely by wave model. The mathematical form of uncertainty principle states that the product of the uncertainties in position and momentum is always larger than some minimum value. So friends, that is it for today. See you in the next lecture with more on quantum physics. Thank you very much.